like that although there is no influence of the one experiment on the other, there is a change in the very conditions for the possibilities of knowledge. There is a very well-turned sentence which I believe Bohr took a great deal of trouble in formulating, and whose meaning is just absolutely obscure to me. So what I get out of Bohr's reply, and certainly what Einstein got out of Bohr's reply, was simply the insistence that we have no right to a picture of the atomic world.
It was John Bell who in 1965 derived a theorem which proved that Einstein's thought experiment could be carried out in practice. John Bell became the judge of the controversy.
At the time of Einstein and Bohr, it was just a theoretical discussion. You could endorse either Einstein's position or Bohr's position, and it was just a matter of taste. And then there was the great discovery by John Bell in '65 that it is not only a matter of taste, because according to the position that you have, at a certain point, you have predictions which are not the same. If you follow Einstein, you have a certain type of predictions. That is to say, you have results in agreement with what is called Bell's inequalities. And if you follow Bohr's position, you have another type of prediction which are in contradiction, in opposition with Bell's inequalities. And this was a good reason for doing the experiment.
In 1982, in Paris, Einstein's thought experiment was put into practice. Aspect's experiment involved the polarization of photons. Polarization means that light oscillates in specific planes. A polarization filter will only permit light to pass if it oscillates in a specific plane. In Aspect's experiment, lasers irradiate the element calcium. This causes two photons to be emitted from the same calcium atom simultaneously. Measuring instruments on both sides register the photons. In order to determine the polarizations, polarization filters are inserted. Sometimes the photons pass through. At other times, they are stopped by the polarization filters. The measuring instruments register the photons that pass through. The polarization filters can be turned so that it is possible to register photons of other polarization directions. Aspect compared the polarizations of the two photons and observed a correlation. If the polarization filters were set identically, both photons would always either pass through or be stopped. How could this correlation between the two photons be explained? One possibility was that the polarizations of the two photons might be predetermined from the very moment of emission. This would be entirely in the spirit of Einstein.
A reasonable picture in the mind of Einstein was to admit that at the very beginning the two particles have something in common. They bring with them a common property until the last moment. And at the last moment, when you make the measurement, the result of the measurement is due to this property. So you have a property at the beginning, then each particle brings the property, and then the result of the measurement depends on the property, and there is nothing spooky in this picture. This was a picture by Einstein.
In order to find out whether the polarizations of the two photons could be predetermined, the respective settings of the polarization filters would have to be different. Then one might expect a certain limit to the number of pairs of photons that ought to pass through. This limit was known as Bell's inequality. Aspect performed measurements of many thousands of pairs of photons. A counter connected to the measuring instruments recorded when both photons passed through. The the setting of the polarization filters was varied in many directions. However, the results of the measurements showed that it was impossible for the photons to have predetermined polarizations at the moment of emission.
If you believe that the property belongs to the photon from the beginning, from the emission to the source, then the result of measurements must obey to a certain inequality that you call Bohr's inequalities. And we have found experimental results violating Bohr's inequalities. So we are compelled to reject the idea that the polarization of the photon was already existing just after the emission.
The experiment thus pointed to the peculiar fact that the photons chose a common polarization at some moment or other after their emission from the calcium atom. Could it be conceivable that an unknown signal would have time to inform the photons about the setting of the polarization filters? Einstein's theory of relativity insists that no signal can be transmitted faster than the speed of light, namely 186,000 miles per second. Aspect was obliged to improve his experiment.
You have to change something on this side fast enough in order to change it before any information has been transmitted to the other side of the experiment. There are 12 meters between both ends of the experiment. It takes 40 nanoseconds for the light to travel from this end to the other end. If I change something in less than 40 nanoseconds, then what I do here will not be known by the apparatus on the other side.
On both sides, Aspect now placed two polarization filters with different polarization directions. And in between them, a specially developed optical switch. The optical switch now sends the photon out to one of the two polarization filters. It cannot know to which. The switch changes direction in a millionth of a second. Everything now took place so fast that even an unknown signal traveling at the speed of light would not have time to inform the other photon.
And when you switch here, this optical switch, from the up to the down direction, everything is equivalent to a single polarizer that you turn from the first direction to the second direction. And all this system is equivalent to a single polarizer that you switch very fast within a few nanoseconds from one direction to another direction. This was a trick used for the experiment.
Once again, Aspect made measurements of thousands of pairs of photons. And he was still able to observe a correlation between the two photons. Either both photons would pass through, or they would both be stopped. This decisive version of the experiment established the paradoxical fact that the photons did not decide on the same polarization until the actual moment of measurement, when they're 12 meters apart, a distance that could have been infinitely greater.
We have found results in perfect agreement with the quantum mechanical predictions. There is absolutely no deviation, and quantum mechanics predicts that this correlation will not change when you go very far apart, even if you go to cosmological distances.
The conclusion of the experiment supported Niels Bohr's contention that the properties of the two particles are not determined until the moment of measurement. This was what Einstein in 1935 found absurd and described as spooky actions at a distance.
brutal fact is that Aspect's experiment confirms quantum mechanics, and it confirms it in this very peculiar situation. So that I'm obliged to admit that the quantum correlations exist in the world, and if we are to explain them and not just accept them as given, if we are to explain them, we are obliged to invoke something like actions going faster than light from one place to another. Now that in itself you could digest, but there is this very curious feature that although I'm obliged to invoke such actions to explain the quantum correlations, I'm also obliged to admit that there's nothing I can do with these. I cannot use these long-range effects to send messages faster than light, for example. That also emerges from the quantum formalism. So there's this strange dichotomy between what I can do. Human actions are limited by locality. The causality is local. And the kind of thing I need to give an explanation of peculiar quantum phenomena. It's as if somebody was playing a trick on us. It's as if behind the scenes. Imagine, for example, that you have a railway system. We know that the trains cannot go faster than light, but you might, by studying the timetable very carefully, discover that during the night, trains have to be returned to their starting point faster than light. So behind the scenes, extraordinary things are happening which we cannot use personally. And this is a dilemma. I don't think we have a good way of looking at it.